part of chapter 3, and right now we're going to discuss protocols. Protocols, we briefly mentioned it in the previous part, they are a necessity in order for communications on a network to be successful. For data to be able to flow from one network to another, protocols are absolutely rudimentary. Let's go look at some of those network protocols that are very important. I already told you guys that in the beginning days of the internet, we had a problem with proprietary standards of networks that made networks incompatible with each other. It wasn't until Vince Cerf and Robert Kahn came up with a protocol called TCP/IP that we actually managed to have a common standard, a global standard for all networks to be able to be connected to each other, regardless of, for instance, selecting wired or wireless media or or different kinds of hardware or software. So TCP/IP was a very important protocol suite and still is because we still use it today. And basically, it enables as an open standard for us to connect networks together pretty easily. So TCP/IP stands for Transport Control Internet, Transport Control Protocol and Internet Protocol. Those two are intrinsically intertwined. If you look at protocols, we can compare them to the rules of human communications. If we are communicating with a friend out on the street, or we are trying to talk to a friend somehow, there's always rules, unwritten rules, that we actually know that we should adhere to and that we actually observe. For instance, one of the rules could be in certain countries, it's kind of uncomfortable for people to be touching each other during conversations. In other countries, it's given. It's something that you regularly do. So these are unwritten rules. It's an unwritten rule that I shouldn't go scream at a person who's very close by to me because the person will perceive that I'm crazy and screaming and upset. So that's basically, those are some rules, and you have to look at protocols in the same way. They are basically just rules for communications, but rules for communications on a data network. And all of those rules, they are public and published as well by different kinds of governmental organizations, such as the International Organization for Standards, or the Internet Engineering Task Force is also one of them. There's a complete overview in your book about all of the governance bodies of the internet. However, you don't have to know all of them. So I won't ask you about the structure of internet governance. It's important to know that there are several different competing and sometimes cooperating organizations at work in order to make these standards living and thriving. So what do protocols, or the TCP/IP protocol suite, actually regulates? In a way, it is also something that we can observe in human communications. So in order for us to be able to speak to each other, we need to speak a common language. We need to have similar grammar structures. We need to be able to speak at the right speed. We need to be able to timely answer whenever another person is talking to us. And we also try to actually, I would say, acknowledge information that the other communicator gives to us. So basically, TCP/IP is very similar. What it does is it encodes messages, so to specific formats. It formats the messages and it makes sure that these messages are encapsulated. We will see in a moment also what that means. It regulates the message size, timing, and delivery options. So basically, it regulates a lot of different specifications for data to travel over networks. If I look at the TCP/IP suite here, we can see that it's going in a downward spiral on this side, and it's going upwards on this side. We call that going up and down the stack. Each of these purple buttons that you can see here, they are a specific layer in the TCP/IP model. And every time you communicate over a data network, let's say that I'm a computer who wants to request a website, what it happens is it starts at the application layer and it travels down the stack to the hardware layer, which is then going to transport the data over the internet, and it gets, on the other end, received by an application letter who's going to strip down the information all the way to the bottom. So basically, this is a little bit how it works, and it makes sense, I would say, especially if you listen to the entire explanation of the TCP/IP model. So let's start with the one that is all the way on the top. It's something that we call application layer. And an application layer isn't exactly the same as the normal applications that you would have on your computer. However, some of them, you can find them also in application layer protocols. Let's think about our example again, where I want to retrieve a website. I want to go to google.com. If I want to go to google.com, I need to have the protocol that is actually responsible for retrieving websites, and that is HTTP, or Hypertext Transfer Protocol. This protocol enables servers to communicate with browsers, and since they speak this common language, they can easily send websites to each other or request websites from the server. So HTTP is not the only application layer protocol. There's also SMTP, IMAP, which are messaging protocols for email. You have FTP, which is file transfer protocol, which actually deals with the direct uploading and downloading of files on a server. We have to imagine this as always like the user would have a application open on their computer or on any of the devices that are connected to the network. So in this case, it could be a browser. A browser is an application, it's a client that actually is going to be able to communicate with that server if the server has the right software installed to be able to deal with its requests. And it goes all via HTTP protocol. That's how you have to understand the first layer, or application layer. What is important also is that once you request a website via one of the applications, so via your HTTP application in this case, it's important to understand that it usually goes like this. It says, I want to download a web page from facebook.com, let's say. However, in this first box here, however, computers are not able to read domain names. Domain names were invented for users. Users use domain names because it's hard for them to remember an entire IP address like it is listed here. Imagine for all of the websites that you have to visit on a daily basis that you have to remember all of those numbers, it would be pretty complicated. You would have to write them down somewhere, but it's not very practical. So that's why they invented DNS and the domain name system. So they made it so that domain names are user-friendly, very easy to remember because they sound like regular words that we use every day. But computers, however, they cannot communicate directly with domain names in the sense that they need an IP address to be able to retrieve a website. So that's where DNS, or the domain name system, comes into place. DNS is a system where you basically have to visualize it like a distributed database, where I have a website, facebook.com. Once I want to load that website onto my browser, it's first going to send a request to the DNS server, which contains a distributed database. And a lot of servers contain different parts of this distributed database. And it's first going to ask the main level servers and the main levels of the database if they have this domain name and its corresponding IP address. So the request gets forwarded. Actually, if it's not within that particular database, it gets forwarded until it actually gets found, and then it retrieves actually the IP address that is associated with that domain name. So that's what DNS does. DNS makes us capable of translating domain names into IP addresses, which is essential for network communications. So DNS is also an application protocol, because it is something that plays it comes into space and comes into play in the application layer. Let's go on to the next layer, and that is the TP, or transport layer. It's also the TCP part of the TCP/IP model. So TP stands for Transport Protocol. And what TP does is it allows for communications between two different hosts on a network to be established. It also prepares data to be sent over the network. In our previous video, we already explained that the way that data travels over a network is through packet switching. That means that every part of data that needs to travel over the network needs to be prepared in advance in order to be able to send packages all over the internet that will then be received by the receiver, who can then recompose the entire picture. So TP helps with that. It segments data into pieces and it prepares it. TP also tries to identify appropriate applications. So it could be possible that at any time you're maybe have a lot of different tabs open on your computer. It could be a mailbox, a mail client, it could be a web browser, it could be an FTP program. So since we have multiple applications at the same time that are running and multiple services from the application layer need to be performed, TP is going to help by just saying, okay, I'm going to give every application an identifier called a port. So for instance, HTTP, which is an application, always goes via port 80. It's a given. So that just helps the computer on the other hand to understand where to look for and how to identify this session. It could be kind of comparable to if I would say to a friend of mine, hey, I'm going to shake your hand on the left-hand side, stick out your left-hand side, and I will do the same thing, and that's how we can communicate. That's basically how you could visualize it. So that's what TP does. So TP is very often confused with TCP. I even have some of those confusions in my presentation as well. And it's done deliberately because I think one of the most common parts of TP that we use is TCP. But we have also another one, and that is called UDP. So both of these protocols, they're a little bit different from each other. So how can we understand this in an easy way? Imagine that you live on a street. On the street, you have a very nice mailman who always goes and delivers your packages, and afterwards he or she knocks on your door and says, hey, did you receive this package? Is everything okay with this package? So they do the effort and they go the extra mile to go and ask you if everything was okay and if you actually got the things that you requested. This is a very nice way of delivering packages. However, on the other hand, let's imagine services or companies such as FedEx or UPS, where speed is one of the most important elements. So what they do is they try to send the package as fast as possible from a sender to a receiver, and that's also their hallmark. That's what they're famous for. So this is how you can compare TCP and UDP. So TCP, Transmission Control Protocol, it actually is that carrying mailman. So TCP, since it's used for websites and for mail traffic, it cares a lot about the packages that it needs to deliver. So after every package gets sent, it also asks for a delivery notification. It kind of says like, hey, did you receive this? Kind of like in the example of the mailman. And when it gets an acknowledgement of the reception, it goes and queries if other packages were received. The reason why that is because for applications that run on TCP, it's important that all of the packages of data actually get delivered. Otherwise, it might not work at all. If you have a lot of packages of a website that do not get delivered, the website might not load. Similarly with an email as well. However, UDP, or the User Datagram Protocol, follows the example of FedEx or UPS, like I mentioned. It's mostly used for video streaming and voice communications over the internet as well. Simply because since it's a lot more data that needs to be sent there, it needs to happen fast, and they don't care so much about it being reliable, because if some of the packages get lost along their way, it's fine. It will still work in the end. So the importance is to remain a steady connection and to remain a steady data transfer with user datagram protocol in comparison to TCP. Then let's move on to the next layer. The third layer in the TCP/IP model is called the network or internet layer. The role of this layer is to deliver packages to a designated IP address. Packages consist of a header followed by a body. The header describes the package's destination and origin. Routers are the most important device for this layer. So IP stands for Internet Protocol Address, and these addresses are very important. Every device that is actually connected to the internet has an IP address. That being said, it's not necessarily true that all of those IP addresses are static, so that they are constantly assigned to one device and they don't change. That is not the truth. IP addresses can change, especially if you're just on a local area network. A user who's behind a home router and who's basically using his own local area network. So what is important is for every data packet that there is, IP is going to actually add a little header on there, and it's going to attach the destination and source of this message in order for a router to actually be able to use this information to efficiently route all of those packages over the network. Let's move on to the next part, what is important to understand. Let's go into a little bit more depth about IP addresses. So IP addresses are kind of like in the format that it's here, and they're made out of a series of up to 4 separate numbers, each delineated by a period. If you look at IPv4, which was a previous addressing scheme that the Internet Protocol would use, we could see that these were in the format of 4 groups of numbers, 174.129.14.120. Every string of number could vary between 1 to 255. So that meant that in total, if you would add all of that up, you could have 4 billion variations of this. IPv4 was invented when the internet was invented. So the reason why we had this 4 billion limit is because nobody in those days thought that the internet would become such a big medium, that the internet would become such a huge platform with billions and billions of devices. However, if you look at today's reality, IPv4 is already not useful anymore, because basically there's already more devices than that. I wouldn't say not useful, it's used a lot still, but what I mean is if you would purely run an IPv4, we'd have already used up all of the available IP addresses within this addressing scheme. So that's not the objective. That's why they actually upgraded IPv to IPv6. And IPv6 is just a little bit more complicated because instead of 4 strings, it actually has 6 strings. And that's actually why it's a little bit more advanced. Also, because of this, what could happen is that you have a lot more devices that are able to connect to the internet. It's not something that could happen, it will happen. So the limitation of this, because it has the same principle, 1 to 255 variations, it could be, the limit of this could be 340 undecillion. It's estimated that this is more than the amount of sand grains on the planet. So it's an important improvement. And I think by that time, by the time that we used up those 340 undecillion, if we ever will, I think the planet will not exist anymore, or at least during that time, I hope if the planet still exists, that we would be intelligent enough to have found a better way of communicating even. What is important to note also about IP addresses is that IP addresses always indicate networks and subnetworks and hosts on a particular network. So every part of the IP address actually means something. Let's go on to the last layer, and that is called the data link layer. The data link layer is responsible for addressing and delivering frames from one computer to another. And it also collects the bits from the physical layer in the form of a data packet. On the contrary to the Internet Protocol or Network Protocol, the data link layer uses something called a MAC address. So we already had an IP address, and now we also have a MAC address. This MAC address is a little bit more stable than an IP address because it's actually burned in onto your network interface card. So it's hard-coded, so it cannot be changed unless you change your network interface card. So a MAC address is important because it is a more, I would say, precise way of finding devices on the internet. I will show you an example also of what a network interface card looks like. So this is one for wired solutions. It's important to know also that we have more than one network interface card. We have one for wired and one for wireless. So network interface cards are crucial because they enable us actually to convert binary data over onto network media, and they also do the opposite way around. And they're the way that we can also find devices on the network. That's what the network interface card does. So without it, you wouldn't be able to connect. Let's look at the last layer. The last layer is called the physical layer. The physical layer deals with all of the hardware devices that are actually included in network communication. So it would be all of the media that we mentioned. For instance, an example of a physical layer device would be a Ethernet cable or a coaxial cable or a fiber optic cable. So all of the hardware specifically, that's what the physical layer entails. In the physical layer, what we have is we have to have a transformation from binary data, the data that the computer uses, and we have to send that over to electromagnetic signals or to radio waves or to fiber optic, depending on what type of connection that you selected. If we go back to the previous model here, let's go back a little bit more up. Here you can see also a sequence of how all of this that I just explained works. So we start off at the top with the application layer, where a message from a client's browser is being sent to a server where it says, I want to download a web page from facebook.com. First protocol that goes into action is DNS, domain name service. So via DNS, we can look up what facebook.com's real IP address is, which then the application layer can use to correctly identify that device. When the message is completed and sent, what will happen is it will go on to the next level, the transport layer. And the transport layer, like I already said, identifies sessions with source and destination ports. The message then becomes a segment or a datagram. It goes on to the next layer, the network or internet layer, and then the data becomes a packet. So remember that we've been talking a lot about packets, and everybody does that all the time. When we are talking about transferring data over the internet, we usually talk about packets. But technically, it's not in every layer of the TCP/IP model you can talk about packets. It's only when the network or internet layer actually comes into play that you can talk about that. As I already explained, then you also have the data link layer, which uses a MAC address, source and destination MAC address, and then the data, when it's prepared, it actually goes over to the physical layer. So you could also compare this kind of to like a mail office, where in the application layer, you're going to be the user who wants to send his mail, and you're going to find a specific way of doing that. Then you're going on to the transport layer, where you actually, for instance, decided to send a box. So all of these boxes are prepared in equal sizes within the transport layer, and then um, it goes through the next layer, where you're actually writing address and source and destination onto that box. And then in the data link layer, you're going to add another more specific identifier, and then you're going to prepare this box to be able to be sent specifically over a physical network. So your physical network in this case would be maybe a bunch of trucks that are owned by the United States Postal Office, or um, anything similar. So I hope you understand a little bit more what TCP/IP is about. It is a little bit of a dry and abstract model, and it could be a little bit harder to understand at first. I would advise you to just go through it carefully and let me know if you still have any questions about this model. For the exam, it's mainly important that you understand a little bit what this means, and I will never ask you to explain the entire model to me, but I could ask questions such as, which one of the following are application layer protocols? And then I give you an entire list of them, and so you have to select which one it is correct. So please try to read this carefully as well, so that you are able to follow along with this, and it would be a lot easier for you to answer exam questions about this then.